So let's see. So hemophilia is a blood disorder in which blood does not clot easily. It is caused by an abnormal gene on the X chromosome, which females have 2 of and men have 1 of. Females may be carriers, but asymptomatic, right? It's on 1 chromosome. Whereas affected males who carry the gene on their only X chromosome are always symptomatic. So if a male has the gene on their X chromosome, they definitely have hemophilia, whereas a female to have hemophilia would have to have it on both X chromosomes. Genetic counselors specialize in calculating probabilities the disease is passed on from one generation to the next. Let's look at the specific example where Bayes' formula is useful. Yeah, actually, it's interesting. I was thinking about this because my father's siblings had cystic fibrosis, and they definitely died of it, and he did not because he didn't have it. So I remember back when my wife and I were thinking about maybe having kids, which we didn't, but when we were thinking about it, I definitely got tested to see if I was a carrier of the cystic fibrosis marker, which I was not, which is great, but we still don't have kids. So anyway, let's see. So here's the setup. A mother of 4 wants to know the probability that she is a carrier of the hemophilia gene. Here's what we know about her. She has 3 healthy asymptomatic sons and 1 healthy daughter. So here's this mother of 4. We use circles for ladies and squares for gents. I don't know why. And she has had children with this other gentleman over here. And their 4 kids, 3 boys and 1 girl, are all asymptomatic. And we use the open boxes or open circles to indicate someone who is affected. We also know her husband does not have hemophilia, but her brother does. And she also has a healthy sister. So right over here, she has a healthy sister and then a brother who has hemophilia. Okay. By the way, for those of you just joining us, we're looking at that same hemophilia problem that he did in class today. I thought it was worth going over again. Here's the handout to the problem written up by Grant. And then, right, they had parents, neither of which had hemophilia, I believe. Yeah, have no symptoms of hemophilia. Okay. So we want to know what the probability is that she has hemophilia. Or that we want to know the probability that she so what's the probability that of A, where we want to know A is a carrier of the chromosome. So we want to know what's the probability of it? What's the probability that she has hemophilia? Well, we can actually refine this because the probability that she has hemophilia, knowing that I don't want to get too into it here, right? But knowing that her brother has hemophilia, her mom definitely had to contribute an X chromosome that was that carried the gene, right? The dad contributes the Y, the mom contributes the X. I think that's how it works. I'll be perfect. That's like my biology knowledge is not super great, right? Yeah, X from mom, Y from dad. So since he has it, mom clearly is a carrier and asymptomatic, so only has 1 gene, that's a hemophilia gene. So sounds like there's a 50-50 chance. If we didn't know anything about her kids, there's a 50-50 chance that she could be a carrier, right? Either her mom passed it on to her or not. But we can actually refine our estimate of the probability that she has hemophilia based on the fact that none of her 3 sons or 1 daughter, mostly the sons, right? Knowing the daughter doesn't have it doesn't really tell us anything else. But knowing that the 3 sons don't have it kind of tells us a lot. So let's write it this way. Let's let A be the probability, or A be the event, I said. A is the event that mom has or is a carrier. Right, we definitely know she doesn't have hemophilia. And then we're going to let F be, and the way this is written is slightly different than what we did in class, but it still gets the same point across. F is the probability that all 3 boys have hemophilia. Okay, so to have hemophilia, the boys at least would have to get it from their mama. Okay, right? Is there something? Okay. Anyway. Sorry, I was trying to like. Okay. Anyway, so they had to get it from their mom. She's not. Well, actually, let's write it. So here's what we really want to find. We want to find the probability of her being a carrier, given that her 3 boys have hemophilia. Or sorry, the probability that they have hemophilia, right? Or actually, sorry, they do not have hemophilia, right? Yeah, that makes more sense because that's actually what's happening. Sorry. So we want to find the probability of her being a carrier, given that all 3 of our sons do not have hemophilia. Okay, so we know how to find that. That's the probability of her being a carrier and all 3 sons not having hemophilia, divided by the probability of all 3 sons not having hemophilia, which we can definitely calculate. We can calculate that as, well, we know the probability of all 3 sons not having hemophilia. If she, actually, we don't know that. We need to work on that. So I think we need a Bayes rule here. So we're going to say that the probability of all 3 sons not having hemophilia is going to equal, this is where we use the law of total probability. Oh, or we could have made, so I like doing it this way, but I also like using the tree. I think the tree diagram is very nice. So let's go ahead and use this here. So either the mom has, disappear, right? Either, the mom has hemophilia or the mom does not have hemophilia, right? And then after that, we have either the probability that all 3 sons are healthy, given that the mom has hemophilia, or the probability that all 3 sons are not healthy, given that the mom has hemophilia. And over here, same deal, probability that all 3 sons are healthy, given that the mom has, or is a carrier. I keep saying has hemophilia, I meant is a carrier. Or the probability that all 3 sons are healthy, given that the mom, are not healthy, given that the mom is a carrier. So let's see what we've got. So 1/2 chance that she is a carrier. So the probability of this is 1/2. Probability of this is 1/2. And then we know that the probability of all 3 sons being healthy, given that she is a carrier, is going to be 1/8, right? There is a 1/2 times 1/2 times 1/2 chance that each son would be healthy, right? First son has a 1/2 chance, second son has a 1/2 chance, third son has a 1/2 chance. So for all 3 of them to be healthy, it's a 1/2 times a 1/2 times a 1/2. And then we don't actually care about this, but this would be 7/8. And there's a 7/8 chance that at least one of them would not be healthy, which didn't happen. And then if she is a carrier, there's a 100% chance that, there's a 100% chance that all of them would be hemophiliacs. So that would be 1 and that would be 0. All right. So now, so again, we want to find the probability of her being asymptomatic or not being a carrier, or sorry, got it. A is being a carrier, right? So A is carrier. F is all healthy. So what's the probability of her being a carrier given this known information that all 3 sons are healthy? Well, that's what we said before. I'm just writing the same stuff out here. It's the probability of her being a carrier and all 3 sons being healthy divided by the probability of all 3 sons being healthy. Okay, let's see what that is. So the probability of her being a carrier and all 3 sons being healthy is going to be 1/2 times 1/8. There's only one way to get there. You got this and you got this. The probability of all 3 sons being healthy is all the paths to get to all 3 sons being healthy. So it's either this and this, which is again 1/2 times 1/8, plus this times, that seems not right. Yeah, what am I missing? Sorry, there's something I'm not quite seeing here. Oh, sorry. Yeah, my brain got it backwards. I'm apologizing here. Sorry. Right. A is being a carrier. A complement is not being a carrier. So if she's not a carrier, sorry, I got it way backwards. There's 100% chance that all 3 sons are healthy, and there is a 0% chance that all 3 sons have hemophilia. Right? Because if she's not a carrier, she can't pass on the gene. So sorry about that. That would be a 1/2 times 1. The thing I like about the tree, assuming you do it right? You don't write stupid things like I just did. The thing I like about the tree is you don't really have to memorize any of the formulas, right? I mean, that's not true. You do have to memorize the formula that the probability of A given F is the probability of A and F divided by the probability of F. But then you can just look at the tree to kind of see the rest. You don't have to know, although I still think you should know, but you don't have to know that the probability of A given F is the probability of A times the probability of F given A. You don't have to know the rule of total probability for F, which is that the probability of F is this times this plus this times this. Are they things you should know? Yeah, probably. But do you have to know them if you can draw this tree diagram? Not really. So it's kind of nice. So we see if you calculate this, you get 1/16 divided by 1/16 plus 8/16, which is 9/16, and that reduces to 1/9. So good problem. And actually, before we do it, so I've got a couple more here. There actually was something else. There was a question someone asked me in their homework today that I thought was a really good question because it kind of really displays how you can make this process super easy on yourself or super hard on yourself. And it has to do with the whole idea of the reduced sample space. So I'm going to make up something slightly different. It's maybe not terrible. So I want to know what's the probability. Well, actually, let me back up a little. Let's say we draw 6 cards from a usual deck without replacement. And we are told that the first 5 cards are hearts. What's the probability? Given that first information, I want to know what's the probability that the 6th card is also a heart. I'm going to show it to you the long way so you can appreciate how nice it is to do it the short way. But I do want you to see, right? So here's the long way of doing it. Let me do one thing here. Hopefully you guys can see all right. I feel like my video quality does not look excellent. So the long way of doing it, so I want to know what's the probability of getting, let's call these events, let's say A is the event that the first 5 are hearts, and B is the event that the 6th card is a heart. Okay, now I want to know what's the probability of B given A. The black pens always run out. Okay, so we can use some red pens. Red's fine. So Well, we know the conditional probability here. It's the probability of A and B, or B and A. It doesn't matter which way you write this, A intersect B. You can also write it as B intersect A. It's the same either way. Divided by the probability of A. Okay, so I want to know what's the probability of B and A. So the probability of B and A, that's just the first 5 are hearts and the 6 cards are heart. So it's the probability that the first 6 cards are hearts. Okay. So the probability the first 6 cards are hearts, well, it's the number of ways of getting the first 6 cards being hearts divided by the number of ways of picking 6 cards. So that's going to be, there's 13 hearts to pick from. So it's going to be 13 choose 6 divided by 52 choose 6. That is the probability of the first 6 cards being hearts. Divided by the probability of A, which is that the first 5 cards are hearts. Okay, the probability of A is, it's the same kind of deal. It's going to be 13 choose 5 divided by 52 choose 5. Not, well, actually, I would say not too terrible, but kind of terrible. I want to simplify this so you guys can see that it's going to be the same as the actually nice way we're going to find the answer. So let's see what we get here. So I'm going to rewrite that as 13 choose 6 divided by 52 choose 6 times, I'm going to multiply by the reciprocal here, so 52 choose 5 divided by 13 choose 5. Okay, so let's write these out. So 13 choose 6 is 13 factorial over 6 factorial times 7 factorial. And 52 choose 5 is 52 factorial over 5 factorial times 47 factorial over 52 factorial divided by 6 factorial times 46 factorial times 13 factorial over 5 factorial times 8 factorial. It's a lot of factorials. Now, what I would recommend doing is flipping and multiplying both of these. So this is really going to be 13 factorial over 6 factorial times 7 factorial times 52 factorial over 5 factorial times 47 factorial times the reciprocal of this, so 6 factorial, 46 factorial, 52 factorial, and then the reciprocal of this, which is 5 factorial times 8 factorial over 13 factorial. And now cancel a 13 factorial with a 13 factorial, and a 52 factorial with a 52 factorial, and a 6 factorial with a 6 factorial, and a 5 factorial with a 5 factorial. And so it looks like we're left with 46 factorial over 47 factorial times 8 factorial over 7 factorial. And no, yeah, okay. I was a little worried for a second. We're fine. So that's going to be, so 46. So someone should be able to tell me what's 46. Oh God, if I don't die from coughing here, sorry. Somebody should be able to tell me in the chat. Whoops, I just closed the chat. Open the chat back up, James. What is 46 factorial over 47 factorial? You guys should all be able to tell me what this is. Like that. Somebody. Thank you, Carissa. Exactly. It's 1 over 47. Somebody else should be able to tell me what's 8 factorial divided by 7 factorial. Somebody besides Carissa. Thank you, Ethan. Yes, exactly. 8. So the answer is 8 over 47. That's a lot of work. Here is the much easier way. So the first 5 cards we drew were hearts. Great. So our reduced sample space now, after the first 5 cards are hearts, is there's a deck of 47 cards, and we removed 5 hearts, so there's only 8 hearts left. 8 hearts and 13 of the other cards. Great. So that's what we're left with after the first 5 cards are hearts, and we want to know for the next card you draw. So if you draw 1 card, what's the probability of getting a heart? There's 8 cards left that are hearts out of 47 cards total. So the probability of the 6th card being a heart, given that the first 5 cards are hearts, is, well, there's 8 hearts left to choose out of 47 cards left to choose from. I hope you all see how much easier that was, because it really is a lot easier, right? If you can get yourself to think of when you're doing a conditional, again, this is assuming that, right, like in an example like this, you can't really do that kind of thing because you can't just say what the reduced sample space is. But for like decks of cards or balls and urns or things like that, where you can be like, oh, I took this many out, what's left? This is a very powerful tool, right? It's much, much, much easier to say, oh, yeah, I took away 5 cards. They were all hearts. There's an 8 and 47 chance that their next card is going to be a heart. So I really, really, really would, again, encourage you all to kind of try to be comfortable with this. I know there's some homework problem. I know there is a homework problem exactly like this, like I changed the numbers in the suit, but there's a homework problem very similar to this. I definitely would encourage you to think of it this way. All right, let's look at a couple more examples here. Sure, I might as well just send you guys the link. So I'm looking at the last problem on this handout if you care to look at it. Also, a reminder to, if you have not already and you still want to please fill out the survey that you can find in the modules of Canvas. Also, actually, on that same note, give me 1 second here. There's one other thing I did want to mention. I did post in Canvas a review of sorts. I just want to show everybody where that is. Canvas is working great. Share my screen, share it up. So if you look in Canvas here, if you look in the modules, you'll see there is a 17C final review, and there's also solutions which I made not available yet. They're going to be available on Thursday, next Thursday. I can make them available sooner if you want me to, but I thought it might be good to give you guys an opportunity to work on the problems without having access to the solutions. So if you find yourself wanting the solutions, send me an email. I'm happy to email it to you if you want them before June 3rd. Otherwise, they'll become available June 3rd. But just to take a look real quick, right, there's lots of good questions that kind of cover the range of topics that we've talked about in this class. I couldn't remember if we did limits as X and Y approach something. So if this question doesn't seem like it applies, like if you don't remember doing something like that, just ignore it. I can't remember whether or not we did limits like that, so I don't remember. But I think every other question here is certainly a valid question that could definitely be the type of thing that shows up on an exam. So that's there for you to work on, and then there will also be solutions posted June 3rd. Or if you want them sooner, you can always email me, and I'm happy to send them to you sooner. I just know, like, for some people, there's the temptation of like, oh, I tried this problem a little bit, I'm not getting anywhere. Let me go look at the answer. Whereas if you don't have the answers right available to you, you might give it more of an effort before you try looking at the answers. I know it's true for me. I know, like, if I'm like, I tried a thing, it didn't work. Okay, let's look at the answers. Let's see where we're going wrong. All right, so let's look at this next one here, which is the last problem on that link I just sent you guys, about color blindness. Color blindness, so like many genetic things, men often get the short end of the stick in some ways because we have one of each, right, X and Y chromosome. And so if something's wrong with the X chromosome, we're kind of screwed, such as life. Color blindness is an X-linked. I mean, I suppose it would also be bad if it was Y-linked, right? If it's Y-linked, you're just totally screwed because only men are getting the Ys in the first place. So yeah, one of each, maybe not the best design, but I wasn't doing the designing. Not that I would have done a great job, but whatever. So color blindness is an X-linked inherited disease. A woman who carries the color blindness gene on one of her X chromosomes, but not the other, has normal vision. A man who, right, just like the hemophilia, right? If the woman has it on one gene, she's asymptomatic but a carrier. If the man has it on one gene, he has the condition, disease, if you will. I wouldn't really call color blindness a disease, but whatever. A woman with normal vision who carries the color blindness gene on one of her X chromosomes has a child with a man who's colorblind. What's the probability that their child has normal vision? So let's see. let's write it this way. So let's let X superscript B be the gene for color blindness. So, I'm sorry. We have a woman. So we have the father and we have the mother. And the father we know has color blindness. So he has the color blindness gene and then some Y gene. And the mother, we don't know, right? The mother is, sorry. Oh, no, we did say that she carries the color blindness gene as well. She carries, but is obviously asymptomatic. So she has one color blindness gene and one not. Great. So we want to know what's the probability that their child would be colorblind. Okay, well, I wonder if we can make a tree. I feel like, so although we could totally make a Punnett square, and there is a Punnett square on the handout, and I would encourage you all to look at that. I definitely don't think from class today, I definitely got the impression that Dr. Lewis, at least in this class, probably doesn't care about you doing a Punnett square or not. So let's try and do it using a tree, because I think trees are where it's at. Everyone loves trees, both mathematical lens and their real kind. So, except for poison ivy. Okay, so let's see. So here it doesn't really matter which. So like I said, most trees, when we're talking about conditional probability, it does matter which kind of branch is first. But here it doesn't. We're not thinking of like the mother contributing her gene first and then the father, or vice versa. It's just whatever. So let's do the mom first. So the mom can either give a colorblind gene or a not colorblind gene. And then from there, so that's mom. And then from there, the father can either give his colorblind X gene or his Y gene. And similarly, the father can give his colorblind X gene or the Y gene. So let's see, this way we end up with a colorblind girl. This way we end up with a colorblind boy. This way we end up with a carrier girl. And this way we end up with a not colorblind boy. So the probability that a child will be colorblind looks like there's a 1/2 probability, right? There's exactly 2 ways of being colorblind. If the father donates, if basically it totally depends on the mom, actually, right? It doesn't really matter what the dad does, because right, if the mom contributes her carrier gene, then it doesn't matter what dad does. Either you get a colorblind girl because he's colorblind, or you get a colorblind boy because she gave the gene and dad was still colorblind and couldn't do it for that. So here we have a 2 in 4 or 1/2 chance of having a colorblind child, which again wouldn't be terrible, right? Colorblindness is, as far as things go, it's not that bad. You know what? I say assumptively, right? I imagine it's not that bad. Who knows? Maybe it's really terrible. I don't imagine it is, but it could be, I guess. So, anything else I want to say about this? We could ask other questions, but I don't feel like we need to. Let's look at one more thing here. Yeah, this one looks a little more interesting. This is a problem from the old textbook. I think this. Let me double check and see if this is from our textbook or from the old textbook before I say it's from section 1. I think this is problem number 7 from section 12.3. Let me double check. Yeah, it is. Okay. So if you're curious, this is problem 7 from section 12.3. And here is the handout to it. This one's a little bit involved. But again, I feel like you might get asked questions that are a little bit involved. So it seems worthwhile to talk about them. Who knows? Maybe he gave this one as an assignment. So here's the setup. And this one's a bit much. So let me take a sip. Muscular dystrophy is a genetic disease caused by a mutation on, guess what? The X chromosome. It's always the X chromosome, right? It's not always X chromosome, really, but it often is, because if it's on the Y chromosome, basically, if it's on the Y chromosome, every man is going to have it, right? And so if every man has it, if it's really debilitating, it doesn't really get passed on because the men don't make it long enough to pass on the gene to someone else. So that's why Y chromosome genetic diseases often kind of don't make it very far, because, right, depending on what it is, depending on how severe it is. So muscular dystrophy on the X chromosome, let's assume with a probability of mu. So we're saying the probability of having the X chromosome mutation, the X chromosome muscular dystrophy mutation is mu, which we also use for the mean sometimes. So as usual, any male child carrying the mutation on the X chromosome is going to develop the disease, whereas only females who have it on both X chromosomes will develop the disease. So first things first, let's list the sample space of possible things that can happen. So our sample space is, you could have a female with both X chromosomes being not afflicted, or a male with an X and a Y where the X is not afflicted. Or you could have a female with the first X afflicted and the second not, or the first X not afflicted and the second afflicted. What else could happen? You could have a female where both are afflicted, and you could have a man where the X chromosome is afflicted. And I think those are all the possibilities, right? There isn't any other way you can have two chromosomes. Right, I'm talking about having muscular dystrophy. So, right, this is because the mom can give an X or an XM, and the dad can obviously give an X, an XM, depending on what, we don't know what he has, or she has, or what. Right, so depending on if the dad has it or not, right, he might be giving that, or he might be giving that. So if he has it, he can give that or that. If he doesn't have it, he can give that or that. Same thing with the mom, right? If she has it, she's given that. If she's a carrier, she can give that or that. If she doesn't have it, she can give that. It's actually the letter mu. It's the Greek letter. Yeah, but yes. So probably so it's probably of having X chromosome mutation for muscular dystrophy, we're going to say is mu, which is a number we don't know what it is, right? We're just giving it a constant name so we can try and figure some stuff out about it. So let's construct a tree diagram for all possible outcomes. Okay, so we're making a new person. And they're either going to, assuming, right, they're, I guess, genetically typical. I don't know what the right words to use are. Assuming they either have an XX or an XY, right? There are people that definitely have other, right? I think people can have like XXY sometimes. There are definitely other genetic types that are viable. But assuming something that is more typical, we're either going to have a male or a female. And we will assume, although it might not be 100% correct, but we'll assume that there's a 50% chance of each thing happening. Okay. So we have a female. There are some options. You can either have, well, let's see. There's 1, 2, 3, 4 ways to have a female. So we're going to have a branch with 4 options here. There's 1, 2, 3, 4 options here. We can either have XX, XXM, XMX, or XNX. And the probability of this, well, probably of having XX is going to be, so the probability of an X is going to be, sorry, like the probability of having a mutated gene is going to be mu, and the probability of having a not mutated gene is going to be 1 minus mu. So XX is going to be 1 minus mu times 1 minus mu, or 1 minus mu squared. XXM is going to be 1 minus mu times mu. XMX is going to be mu times 1 minus mu. And XMXM is going to be mu times mu, which is mu squared. Okay. And then for a male, there's less options. There's still like 2 options, right? You can either have a mutated gene and a Y, or a not mutated gene. And not mutated doesn't get the N on it, right? So we can either have X and Y. So the probability of this is going to be mu. Probably this is going to be 1 minus mu. Great. So then let's talk, and again, right? So this is the probability of X, the probability of yeah. That's what I was saying. So let's ask a question. What's the probability that, let's say we had a kid that, and again, both parents, yeah. Let me actually read something here real quick. 1 sec. I feel like this next question is not a great question, but still. Well, yeah. So actually, Ethan, we're going to talk about that right now. Yes. So what's the probability that a person, a kid, has muscular dystrophy? Well, it's going to be all the ways of having muscular dystrophy. So let's see. There's this one here. So that's the probability of getting that is going to be 1/2 times mu plus this one here, which is going to be 1/2 times mu squared. Essentially, I was writing these as conditional probabilities, right? This here is the probability of XX given that you're a female. This here is the probability of XXM given that you're a female, which is often what we do when we make a tree diagram, right? You write each set of probabilities as what they are at that level, not like what they are times the thing before it. So let's ask another question. What's the probability of muscular dystrophy given that the child is a male? Okay, so this actually, again, this is where we want to kind of use our common sense, right? We're on this branch. We're given that it's male. So given that it's male, what's the probability of muscular dystrophy? Well, it's going to be mu, right? Or you could do it the long way, right? You could say it's the probability of having muscular dystrophy and being male divided by the probability of being male. So the probability of muscular dystrophy and being male is going to be 0.5 times mu And the probability, right, 0.5 times mu. And the probability of being male is going to be 1/2. You can also use the law of total probability, but you don't have to, right? You can say, oh yeah, probability of being male is 1/2 times this plus 1/2 times this, but that's exactly 1/2. But those cancel, and you just get mu. All right, let's ask a more interesting question. What's the probability? Well, in fact, I think we can see the answer already. Let's go ahead and take a look. What's the probability of having muscular dystrophy given that you're female? Well, given that you're female, it looks like mu squared, right, is the probability, right? Because there's only one way of getting it, and the probability of that is mu squared. So who has a bigger chance of getting muscular dystrophy? The females with the probability of mu squared or the males with the probability of mu? Good question. So it's actually the males, right? Because in this situation, mu has to be between 0 and 1, right? Mu can't be a number that's greater than 1, because then we'd be saying, right, if the probability of having X chromosome is mu, you can't have more than 100% probability of having the muscular dystrophy mutation. So, right, mu is less than 1, bigger than 0, which means mu squared is less than mu. So that probability is less than that probability. So I think that's all I really have. I know we have 5 minutes left, but I think I've said all the things I have to say. We have class next Wednesday. That's it, right? There's only one more class. My intent is to do some review work, probably kind of look back at previous things, probably very possibly go over the review I posted, although we might not get through all of it. But if there is anything specifically you would like to see on Wednesday, like if there's any topics, you're like, James, I'd really like to talk more about solving nonlinear systems with differential equations, I can definitely make that happen. Shoot me an email if there's something that you're like, James, I would really like to see blank. Or you can even write a discussion post if you wanted to. But yeah, the plan for Wednesday is just to kind of go over older stuff, refresh our memories about what we've done all quarter, and then you guys get to study for the exam. When is your final exam? Just write that down. June 9th. Great. You know what time it's at, Vinny? Wait, our short test 3. I don't believe so, Max. So, oh yeah, right. So next Wednesday, you guys have a short test, right? Yeah. So next Wednesday, you guys have a short test. I have to imagine it's on all this probability stuff. I would say for your short test, I have to imagine, like, I would be really, really, really surprised if he didn't ask you a question or he asked you to flip the conditional probability, right? So like, you know what? Let's run. We got 4 minutes. Let's make. So I would be shocked. I would say shocked. I would be shocked if he didn't ask you a question like this. And if not on your short test, definitely on your final. Oh, and the nonlinear differential system. Okay, wow. Thanks, Karina. So I would imagine he would probably ask you one of the questions where he says, like, you know, the probability of having a positive test given that you have the disease is 99%. The probability of having a positive test given that you don't have the disease is some low number like 5%. And then usually they give the prevalence of the disease, but they can also give you the probability of testing positive. So they either give you the probability of having a positive test or the probability of having the disease. And then usually the most important question that he's emphasized this so much, I have to imagine he's going to want to know what's the probability of having the disease given a positive test. That's the question I would assume he would ask. I can't guarantee it, right? I'm not him. I don't know. But if I was a guessing man, if I was a betting man, I would bet there would be a question like this. Specifically where you're given, let's say the prevalence of the disease is, I don't know, 1 in 2,000. Okay, so if I want to know the probability of the disease given positive test, well, I'm going to make a tree. Again, you can do it just using the rules, but I like the trees. So trees, right, you either have the disease or you don't. Probability of having the disease is 1 out of 2,000. Probability of not having the disease is 1999 out of 2,000. And then from there, you go to, I either have a positive test or I don't. Have a positive test or I don't. And then probably having a positive test, given that you have the disease, is 0.99. I don't care what that is, although it's 0.01. Probably having a positive test, given that you don't have the disease, is 0.05. I don't care what that is, although it would be 0.95. And then, right, the probability of having the disease given a positive test is the probability of having the disease and a positive test divided by the probability of having the disease. Okay. This times this is the probability of having the disease and a positive test. And then this and this, or this and this, is the probability of having a positive test, right? You can either have the disease and a positive test, or not have the disease. Remember the or and have a positive test. So have the disease and multiply a positive test, or add don't have the disease and multiply have a positive test. Which is just Bayes' rule, but just found through a tree as opposed to just memorizing the rule. I definitely prefer doing it with a tree. So I really, really could imagine he would ask you a question like this.